Welcome to the Chapter 6-7 Homework Solutions screencast. So obviously I post these as a PDF as well. I think we went over many of these on Friday in class. And these were pretty challenging. So you definitely need to put some time in to gain that understanding. So for Q11, there was somebody shot out of a slingshot or something like that, but in a box. It was asking what the weight would be. Well, the apparent weight would be 0, but the gravitational force was still 750 newtons because the person was in free fall. So it was a little bit confusing or inconsistent in terms of how they asked you to answer that. You had a hand pushing down on a book for question 13. Therefore, the normal force of the table on the book is greater than mg because it must equal both the force mg down and the force of the hand down. So for problem 31 in chapter 6, I assume g was 10 meters per second squared. The elevator's initial motion was down because the apparent weight was less than what most of the trip was. If you think about an elevator, it's only going to accelerate in its first and last parts, where it's speeding up or slowing down. So what I ended up doing first was recognizing that since the force was lower than the force in the middle of the trip, the elevator had to be accelerating downwards. I figured out the mass of the person, 750 newtons divided by 10 newtons per kilogram, gave me 75 kilograms. I don't know why I have a bracket around here and then not the other side. I could figure out the acceleration downward was 2 meters per second squared. Why? Because if I looked at my weight was equal to m, or the apparent weight, or the normal force, I guess I should say, would be equal to mg minus a. So that acceleration downward was 2 meters per second squared. And then to figure out how far the elevator traveled during the 12-second trip, I had to recognize it was speeding up from 0 to 2 seconds, constant speed from 2 to 10 seconds, slowing down from 10 to 12 seconds. And there's a symmetry to this problem, so 4 meters during the first 2 seconds, 32 meters during the middle time, 4 meters during the last 2 seconds. And the reason there is that symmetry is because, as you can tell from the graph, the normal force changes by the same amount, therefore that says the acceleration has to be the same size in magnitude, that is. 35 was a quick calculus problem where you're taking a derivative. Hopefully those are pretty easy. So I did the second derivative of the position function, so you could say, or you could just take the derivative of the velocity equation, which you had taken from the position equation. Either way, it comes out to 12t minus 6 meters per second squared. So if you put in 0 seconds, we get negative 6 meters per second squared. Go back to Newton's second law, F equals m times a. 2 times negative 6 is negative 12 newtons. Down here, positive 6 meters per second squared, positive 12 newtons. This one I thought was kind of challenging, but I think it was explained pretty well by one of the weights in class, so that was nice. Tension is just mg of this. So it got 58.8 newtons. That's the same tension everywhere in the rope if it's a massless rope. At this particular point of interest, the forces down and the forces up have to be equal. The force left and the force right has to be equal. And that force right is what's going to be known as the traction force. So at point B, I'm going to start with F up equals F down. F down is equal to the weight of the foot plus the vertical component downward caused by this tension in the string. And so that's my mg of the foot. T sine 15 degrees is the downward component of the string's tension. We already knew that tension was 58.8 newtons from step A. So that's somewhere around 54-ish newtons, 54.4 newtons. So then the sine of the angle is equal to 54.4 for 58.8. That gets me this angle of 67.7 degrees. Why is that? Well, because the upward force and the downward force must be equal here. To find the traction force, we want to find the horizontal components of both these tensions to the right, and that would equal the traction force. So 58.8 cosine of 15 degrees plus 58.8 cosine of 67.7 degrees. And, I don't know if I did that here. Let me take a look. I may have added that later when I screwed up or forgot about it. Opening up the book. 79-ish newtons. Change that to black so you can actually read it. Ugh. Goes down here. Okay, P55, you've got the wall, you've got the force pushing upward and to the left, so that's causing a normal force as well as an upward force. The normal force is the 12 cosine 30 degrees, 10.4 newtons. The upward component is going to be 6.0 newtons. I had initially forgotten to do that. The friction force is mu times the normal force, so that's 5.2 newtons. Well, gravity is acting downwards on a 1 kilogram mass, 9.8, minus the frictional, minus this force upward would be 3.8 newtons net downward force if we just look at the applied force vertically and gravity vertically. But there's friction also, and friction could be up to 5.2 newtons. So therefore the book will not accelerate and will not move. Remember, static friction is up to a certain coefficient. It is not always that coefficient. Chapter 7, the questions here should have been pretty straightforward. The scale will read 5 kilograms. Why? Because the tension has to be the same as whatever weight is pulling on either side, since there's zero acceleration. This is kind of goofy, but funny question. So the forces are internal to the system, which is why the cart won't move. Question 9, tug of war team can win by how much they interact with the ground. So the friction and the weight they have, which causes a normal force of the ground, would benefit a winning team. For problem 9, you've got a car pushing a truck. It's pushing with 4,500 newtons, so you can find the acceleration of the whole system by taking that force dividing by the mass. And then, actually it didn't say it's pushing the truck with 4,500 newtons. It says it's pushing on the road with 4,500 newtons. So that means the whole system's accelerating 1.5 meters per second squared. So if you apply that to the truck, that means that the truck's mass of 2,000 kilograms accelerating at that 1.5 meters per second squared means that the car has to be pushing the truck with 3,000 newtons of force. Since it's an interactive force pair, the force of the truck must be back on the car with the same 3,000 newtons. Therefore, the net force on the car forward would be 4,500 newtons from the ground minus the 3,000 newtons pushed back from the truck. That's 1,500 newtons of net force on a 1,000 kilogram car, so it therefore has the same acceleration as we found earlier. That's an example of an acceleration constraint. Problem 18 was discussed in class. I like the way that the people who solved it in class did that, realizing that the horizontal components all have to be the same, so that was pretty nice. I focused on this end first and the vertical components. This was given, theta 1 was given as 20 degrees. So T1 sine of 20 degrees equals mg here. And so therefore I could solve for T1 was 57.3 newtons. When I did that, I could figure out that the horizontal component of T1 would be 57.3 cosine of 27 degrees. That would actually also equal T2. That would also equal the horizontal component going to the right on T3, and the vertical component of T3 would equal 39.2 newtons, which is the vertical weight of the dog, or the downward. So the 39.2 up and the 58.3.8 to the right allow me to get this angle, and that's a 36.1 degree angle. This one was a little sneaky. You would think it would just be 2 meters per second squared, but there is an acceleration on the larger ship because forces are interactive. So it means it's a slightly different answer than you'd expect if you just plugged in 2 meters per second squared for the acceleration. So a little tricky. Chapter 7, for problem 28. ended up getting something slamming into a person's forehead or cheekbone. Mass, I think, was a baseball, going from 30 to 0 meters per second in 1.5 milliseconds. So the acceleration is the dv/dt, which was 20,000 meters per second squared. If I apply that with a mass, it's 2,800 newtons of force for both A and B, and that would not crack the forehead, but it would probably crack the cheekbone, based on the information given. 35 was a really nice problem. I think we went over that in class pretty well, but there are 3 frictions, and 2 of those frictions are interactions between the top block and the bottom block, caused by the normal force of the top block and the coefficient of friction of it. So I go through and I note that the friction of the surface on the lower block here is by the whole mass of 3 kilograms times 0.3 is your coefficient of friction times 9.8 newtons per kilogram, 8.82 newtons. The force of friction on the top block from the bottom block, 0.3 coefficient of friction times 1 kilogram mass times 9.8 newtons per kilogram, 2.94 newtons. This is an interactive force pair, friction of the lower block on the upper block. So overall, so take those 4 forces, 20 newtons applied, minus the 3 friction forces, all that over the 3 kilograms mass of the total system. And I get 1.77 meters per second squared. Problem 46 is a Bosun's chair. Pretty cool example. You could see something like this on an AP exam, but basically there are 2 forces upward, so drawing this free body diagram really helps. Technically, these 2 areas should be slightly longer than this arrow downward. Not sure if I drew that very well, because it says this is an upward acceleration of 0.2 meters per second squared. So if we include the mass of the chair and the person, we get a total mass of 80 kilograms. That means I have a net force of 16 newtons up. So 2t, which is upward, minus mg downward would equal 16 newtons. That lets me find that the tension anywhere in this rope is 400 newtons. Hopefully this helps, and you make sure you have the corrections by our next test.